I'm Tian from Huazhong University of Science and Technology. Today, I'm going to present our work towards high-throughput and low-latency billion-scale vector search via CPU and GPU collaborative filtering and re-ranking. This work was conducted in collaboration with Huawei. The content of this talk is divided into 4 parts from the beginning of background to the end of conclusion. The vector search, also called top K nearest neighbor search, refers to finding the closest vector to a given query vector within a dataset. In this context, let's consider a dataset consisting of n vectors, where each vector is represented by a d-dimensional vector. Given a query vector, the goal is to identify the top K vectors in the dataset such that the distance is minimized. Since the curse of dimensionality of ANNS, many approximate nearest neighbor search algorithms has been proposed. We called ANNS, which can be divided into 4 categories: brute force, hash-based, tree-based, and graph-based. Graph-based approaches have demonstrated the promising performance and accuracy for ANNS service. It constructs a proximity graph. Vectors are abstracted as nodes, and edges are deemed as the distance between 2 nodes. For each query vector, the algorithm navigates the graph from a given node and sequentially traverses neighboring nodes that are likely candidates of approximate nearest neighbors. With the rapid development of large language models, ANNS applied to retrieve augmented generation has become a common and powerful move to expand the knowledge base of large language models. However, with the explosive growth of vector from embedding unstructured data, ANNS algorithms need to process datasets containing billions of vectors. Consequently, in-memory ANNS such as graph-based approaches demand substantial memory space, which significantly increase the total cost of ownership of data centers. To reduce the memory consumption in large-scale ANNS, Microsoft's commercial ANNS system, SPANN, introduced a hierarchical index and stores the majority of the index on SSDs. Specifically, during the offline phase, SPANN employs a clustering algorithm to partition the dataset into multiple posting lists. Additionally, to ensure the quality of clustering, it replicates boundary vectors into adjacent posting lists. Then it stores all posting lists on SSDs, while maintaining a central rows of these posting lists in memory using a graph index. Upon a query, SPANN traverses the in-memory graph to identify top M nearest posting list and allows them to host them in memory. Then it finds the top K nearest neighbors when this M posting list via distance calculations. However, we find that although SPANN achieves low latency comparable to in-memory ANNS approaches, its throughput is quite limited. As shown in the left figure, SPANN achieves the peak throughput using only 4 CPU threads and count scale with more threads. Further, we count the query latency in 2 stages. First, the graph traversal in memory, and second is processing posting list from SSDs. As shown in the right figure, the latency of graph traversal increased significantly with the number of threads. The reason is that the multiple queries concurrently read many and large-size posting lists from SSDs, resulting in several I/O conditions and high latency. The product quantization, we call PQ, is a promising way to compress the raw vectors from high dimension to low dimension, thus reducing the size of I/O requests. However, PQ converts a distance calculation between vectors into multiple memory access operation, and thus pose a significant challenge for traditional CPU-based computing architectures due to the relatively low bandwidth of DRAM and limited parallelism. Therefore, the PQ is usually accelerated by GPU because it can fully utilize their massive GPU kernels and high bandwidth memory to improve the query performance. Intuitively, one can adopt hierarchical indexing, product quantization, and GPU acceleration techniques together to achieve an optimal ANNS solution. While we have found that it is no easy task. Here, we first discuss the straightforward solution using GPU-accelerated ANNS solution using PQ and hierarchical indexing techniques. Upon a query, the ANNS engine first traverses the navigation graph to identify top M nearest posting list, and loads this raw posting list or compressed posting list to CPU main memory or GPU's HBM for distant calculation. Since PQ has a negative impact on query accuracy, we add a re-ranking process to improve the query accuracy. During ranking, the raw data of the top n candidate vectors should be compared with the query vector to find the final top k nearest neighbors. Disappointingly, we found that above solutions don't achieve expected high performance, including the latency using single thread and the peak throughput using multiple threads. The first challenge is that the extensive data transmission across devices. We first measure the I/O numbers and the data volume transferred across SSDs, main memory, and GPU's HBM required by each ANNS query on average. As shown in the left figure, although the PQ technique can reduce the I/O size of posting lists from multiple pages to one-page granularity, it increases the number of error requests by 17% due to the re-ranking size. Moreover, a large volume of posting lists are transferred between CPU and GPU, thereby offsetting the benefits of GPU acceleration. The root case is that the GPU's HBM still can't accommodate all posting lists compressed by PQ, allowing extensive data transmission between CPU and GPU to become a new performance bottleneck. Second, to achieve the same level of query accuracy, a re-ranking process is usually required to refine intermediate results. However, we found that the minimum re-ranking numbers are very distinct for different ANNS queries. This significant variance usually causes unnecessary I/O operations and distance calculations if the number of re-ranked vectors is fixed for all queries. Third, the re-ranking process introduces a number of I/O requests to raw vectors on SSDs, but the size of a raw vector generally is hundreds of bytes, while the smallest operating unit of modern NVMe SSD is typically a page. This mismatch in granularity causes significantly read amplification, resulting in extremely low I/O efficiency during ranking. To tackle the above challenges, we propose FusionANNS. It is a CPU and GPU cooperative processing architecture for billion-scale ANNS. FusionANNS includes three key designs: multi-tiered index structure and the CPU-GPU collaborative filtering, heuristic re-ranking based on the lightweight feedback control model, redundancy-aware I/O deduplication based on the optimized storage, each addressing a specific challenge. At first, we adopt the hierarchical balanced clustering algorithm to iteratively partition the dataset to several posting lists. Each posting list contains multiple vector IDs and the corresponding vector content. After the dataset is clustered, we build a navigation graph index using the centroids of all posting lists and store it in main memory. More importantly, unlike SPANN that stores all posting lists on SSDs, we extract only vector IDs of each posting list as metadata and store it in memory. When the graph index and metadata are generated, the intermediate posting list can be discarded. Since the memory footprint of the graph and metadata is relatively small, we can support billion-scale ANNS in a memory cost-efficient way using general-purpose servers. Since PQ can significantly reduce the memory footprint of high-dimension vector via loose compression, even an entry-level GPU can accommodate all compressed vectors in its HBM for billion-scale datasets. In FusionANNS, we pin all compressed vectors in HBM, avoiding data swapping between GPU and CPU. Upon a query, the CPU traverses the in-memory navigation graph to identify the top M posting list nearest to the query vector. Then the CPU consults the metadata to collect the vector ID within this candidate posting list. After that, the CPU transfers these vector IDs to the GPU and invokes GPU kernel for further processing. When the GPU receives vector IDs, it first reads the corresponding PQ vector for each vector ID from the HBM and compute the PQ distance between it and the query vector. Subsequently, the GPU sorts all distance in ascending order and returns the top n vector ID to the CPU. Since the intermediate result obtained using PQ vectors are not precise, the CPU reads the raw vector according to these vector IDs from SSD for further re-ranking. Finally, the CPU returns the final top k nearest neighbors. This CPU and GPU collaborative filtering mechanism can filter out the most irrelevant vectors while avoiding the transmission of vectors contained between CPU and GPU. To reduce unnecessary I/O operations and computations, we propose a heuristic ranking mechanism. The key idea is that when all top k are found, the subsequent re-ranking will not change the top k result. We first divided the re-ranking process into multiple mini-batches and executed them sequentially. During this process, we use a priority queue to maintain the current top k nearest neighbors. When a mini-batch is finished, we calculate the change rate of the priority queue and terminate the re-ranking process if the change rate for successive mini-batches are smaller than a given threshold continuously. To further improve I/O efficiency, we first store high similar vectors on same page to improve spatial locality on SSDs. We designed two I/O deduplication mechanisms, including merging I/O operations mapped to the same SSD page within a mini-batch, and exploiting the DRAM buffer to eliminate redundancy I/O operations in subsequent mini-batches. Here we use a simple example to describe these mechanisms. Amuse that there are two mini-batches in the re-ranking process, where the task of mini-batch 0 is to re-rank vector 2, vector 4, and vector 6. The task of mini-batch 1 is to re-rank vector 5, vector 8, and vector 9. When mini-batch 0 is executed, it first consults the mapping table to obtain the SSD page IDs corresponding to the request vector. Since both vector 2 and vector 6 are stored in the same SSD page 0, we can merge these two I/O operations and only read one SSD page to get vector 2 and vector 6. Since page 0 and page 2 don't exist in DRAM buffer, we directly read them to the DRAM buffer via two I/O operations. In mini-batch 1, although vector 5, vector 8, and vector 9 are stored in different SSD pages, the DRAM buffer already contains page 2, which includes vector 5. Therefore, mini-batch 1 only needs to read page 1 and page 3 via two I/O operation. This is FusionANNS architecture with CPU and GPU cooperative architecture, including offline index construction and online query processing. Next, we conduct extensive experiments, and I will show the key result here. We compare FusionANNS with three representative ANNS solutions designed for billion-scale datasets, including two SSD-based solutions and a GPU-accelerated in-memory solution. Besides the native SPAN and disk-n, we also compare FusionANNS with GPU-accelerated SPAN and disk-n, which exploit the GPU to accelerate the distance calculations. Our experiments are conducted on server equipped with NVIDIA V100 and a Samsung SSD, and we pick 3 billion-scale real-world vector search datasets. For SPAN, FusionANNS achieves same low latency while achieving up to 13 times improvement in throughput. Compared to disk-n, which trades latency for throughput, FusionANNS still improves the throughput up to 4 times. The SPAN GPU and disk-n GPU show even lower performance than the native SPAN and disk-n, since the cost of extensive data movement offsets the benefits of GPU acceleration. More importantly, for the GPU-accelerated in-memory solution RUMMY, FusionANNS achieves up to 5 times higher throughput with similar low latency. To evaluate the performance scalability of different ANNS systems, we increase the number of threads exponentially by a factor of 2. The result shows that FusionANNS demonstrates the best of scalability. We further compare FusionANNS with other ANNS systems in terms of cost and memory efficiency. As shown in the table, FusionANNS demonstrates the best cost and memory efficiency. Okay, in summary, FusionANNS is a CPU and GPU cooperative processing architecture for billion-scale ANNS. It achieves high throughput, low latency, cost efficiency, and high accuracy simultaneously using only one entry-level GPU. Thank you for listening.